All right, chemist. I'm guessing it's the middle of the winter right now. By the time we get to this, I will say this is the end of the summer in which I'm recording this, so it's probably about 90 something degrees out today, and I'll be wishing for those days when by the time you get around to this where it's winter. But this is the end of our second unit, and we're going to start again with reviewing bonding types. I know we've gone over this again and again and again, but this is one of the fundamental basic ideas of the course, is remembering these different types of bondings and really understanding them. So metallic bonding, this is valence electrons shared in a pool. So they're free to flow. Because they're not attached to any one atom. Ionic, valence electron or electrons transferred from the weak metal to strong non-metal. Forms plus and minus ions that arrange into a 3D lattice structure. Remember that they're that alternating plus minus. So molecular covalent atoms share valence electrons. This is, and when two or more, and this could be up to tens of thousands, millions, bonded together equals a molecule. That's the representative particle for a molecular covalent attraction. So there's going to be a lot in this, and let's talk about boiling point and intermolecular forces. So we have our metallic bonding on the left, our network covalent on the second to the left. Now, if we look at molecular covalent, we have shared electrons within the molecule, but no shared electrons between. So the shared electrons are within but not between. This is one molecule right here. So when you boil a molecular covalent substance, you do not break covalent bonds. You only disrupt the intermolecular forces, right? It's not like network covalent. You try to melt a diamond, you have to break those covalent bonds because all of the atoms are covalently bonded to one another. But when you have molecular covalent, those molecules can split apart from one another. All you're doing is breaking the intermolecular forces. And in ionic bonding, you have these alternating pluses and minuses. So in order to boil an ionic compound, you really have to overcome strong attractions. That's why you don't see liquid ionic compounds or liquid network covalent substances. But you do see molecular covalent solids, liquids, and gases, because the only thing holding them together are the intermolecular forces. So how do the boiling points compare? Well, metallic and ionic are much higher. This is true of network covalent too. Much higher BP than molecular covalent. So you have these full positive and full negative charges, large attractive forces. right? From our Coulomb's law, the larger the charge, the more the force, so they're going to be stuck together a lot more tightly. In molecules, however, your attraction is only based on partial positive and partial negative charges. Smaller charges leads to weaker attraction, leads to lower boiling point. So to understand the properties of these molecules, if you can look at the attractive forces that hold the molecules together to other molecules, that will help you. All right, this is going to be a long one, so you're probably going to want to pause once or twice, take down the notes, but there should be quite a bit here. So what is the relationship between boiling point and IM forces? Well, stronger IM forces leads to a higher boiling point. This intuitively makes sense. The stronger the molecules are attracted to one another, the harder they are going to be to separate. So that it's really, when you're changing phases, you're separating molecules. When you're boiling something, you're putting in energy to split them apart from not a molecule, but you're taking the molecules and splitting them apart. Each molecule stays the same. So let me just draw that out real fast so I'm confusing myself. If I have water, I'll just use 3 molecules, and I apply heat, well, when it boils, let's notice the lower water level, I don't get O and H atoms, I get molecules of water that no longer are attracted to one another. Okay. Stronger IM forces, higher boiling point. And remember, this is the intermolecular forces are between molecules. So again, we're not breaking any covalent bonds. The molecules stay intact as individual units. They just separate from the other molecules, just like the water right here. Okay, so as you were doing the work in class, you learned something, that as molecular mass increases, the boiling point increases. So the IM forces must be stronger. And you made a graph that looks something like this, which was molecular mass. Was it? Nope. It was boiling point and molecular mass. And you got something that looked like a very straight line. And the reason this happens, well, let's look at the reasons why. Could it be gravity? You have these larger molecules, maybe gravity's pulling them down more tightly. Well, that can't be it. So boiling point is the same regardless of gravity. Now, some of you astute listeners out there might say, hey, but I've been to Colorado and or a high elevation place. I was told that the boiling point is different. That's true. That has nothing to do with gravity. It has to do with the atmospheric pressure pushing back. So when we talk about gases later in the year, maybe we'll talk about this a little bit. But boiling point is the same regardless of gravity. If you tried to boil water in space, you'd have the same boiling point as you do on Earth, as long as you have the same atmospheric pressure. So it's not gravity. So what you get is that even for non-polar molecules, things that don't have permanent partial pluses or minuses, these molecules we find are polarizable. So what we get, so at any random instant, remember, electrons are always moving. At any random instant, the electrons might move to be preferentially to one side of a molecule or the other. So you notice here that this is just an individual atom. So here's the nucleus. So we have this side is partially negative, and this side is partially positive. Now that is only temporary, right? We call that a random dipole. But it exists for a short period of time. So due to random movement of electrons, one side is partially negative and one side is partially positive. So now what happens when the surface of that one comes near the surface of another? Okay, so you notice how this side is partially positive, this side is partially negative. Now in that instant, when that molecule approaches another molecule, the partially positive side will attract the electrons, pushing the partially positive to the other side. Now this is happening over and over all the time in molecules. So even molecules that are nonpolar are slightly attracted to one another because of the random motion of electrons. So this is a huge idea. Dispersion forces caused by random movement of electrons that cause temporary dipoles on the surface of neighboring molecules. So really these are really small partial pluses, partial minuses that are attracted. They're much smaller than in polar molecules because they're only temporary and they're very slight, but they will exist temporarily. Any two molecules will have dispersion forces. So even polar molecules with permanent dipoles will have moments where their electrons are moving around that actually slightly increases the strength of attraction. And the bigger the molecule, the stronger the dispersion forces will be. You have more electrons moving, more chances for random spots of polarity. So the bigger the molecule, the more dispersion forces you'll get. That's why wax, which is a nonpolar molecule, is a solid at room temperature. Even though it's nonpolar, the molecules are so big that the random motion of electrons, random movement, I was trying to say, or motion, will allow them to stick together. So explaining the trend, greater molecular mass leads to larger molecules, which leads to greater dispersion forces because there's more electrons, more random motion, which leads to stronger IM forces / attraction. So they have greater attraction to each other. If they have a greater attraction, they therefore have a higher boiling point. Okay, so IM forces review. In class, this might be a couple days, but I'm going to do it all in one lecture. So only polar molecules experience dipole-dipole forces, which are the attractions between permanent partial plus, partial negative charges in polar molecules. So that dipole-dipole attraction occurs because you have permanent partial positives and permanent partial negatives in polar molecules. The larger the partial charges, the stronger the attraction. So a molecule that is more polar will be more strongly attracted than one that is less polar and therefore have a higher boiling point. Now we're going to talk about something that my colleague Mr. Hamill has renamed. In your textbooks, it's not really in our textbook now, but when you get to biology and if you study chemistry in the future, you're going to learn about something called, unfortunately named, what do I want to put, AKA, something called hydrogen bonds. Now, it's unfortunate because hydrogen bonds makes you think that it's actually a bond, like a covalent bond or ionic bond or metallic bond. But really, we're going to call it an Estebov. So this is another intermolecular force. It's an IM force. It's not a covalent bond. It's not an ionic bond. It's something that holds molecules together. And it only occurs where H is covalently bonded directly to N, O, or F. When this happens, N, O, and F really pull tightly on H's valence, on the shared electrons. So it gives H a very, very large partial positive charge. And this makes the dipole attraction between H and another N, O, or F especially strong. You saw this when you were looking at the boiling points of things that had Estebovs. And what is an Estebov? Well, Estebov is an extra strong dipole attraction because of positive hydrogen. You can call them hydrogen bonds. You can call them Estebovs. Estebov just sounds funny. So what does this actually look like? Well, so we have put a water molecule here. And then we will draw in another water molecule. Now, if I draw this dotted line right here, those are not electrons. That's a dotted line. This is an Estebov. It is a connection between molecules where one molecule is attracted to the other. So I'm going to ask you how many Estebovs are present in this diagram that I've put up here. The answer is only one. You might want to say that these are also Estebovs, but no, those are covalent bonds. The covalent bond holds an individual molecule together. An Estebov connects two molecules. The covalent bond is much, 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 much stronger than an Estebov. Which is why when you boil water, you don't split apart water into individual H atoms and O atoms. You break the Estebov and the molecules stay together. So why are they so strong? Why do they need their own special designation? So if I look here, I have water and water. I have a very partially positive H and a lone pair on the O, very partially negative, so they can be attracted. Well, if I look at phosphorus trifluoride, this is still very partially negative, but the P now has a lone pair on the top. So while this is partially positive, the lone pair weakens the attraction. So it only works with hydrogen because hydrogen doesn't have a lone pair on the opposite side. There's no lone pair because hydrogen only has those two shared electrons. And those shared electrons are getting very close to oxygen. So the H is very partially positive. Well, let's look at that visually because I think that's a little confusing. If we look at HF versus IF. Now, the colors here show the dark blue is very partially positive. The dark red is very partially negative. So partially negative, partially positive. So in HF, you can see the left side is very blue, the right side is very red. Well, if you look at IF, you'll see a lot more of that green, which is pretty neutral. You get some partial negative on this side, some partial positive on the other side, but it's not nearly as distinct. The partial positive is a lot weaker in IF because of the lone pairs. The lone pairs weaken that partially positive charge, right? So the attraction due to only the dipole forces is a lot stronger in HF than it is in IF because of this unshielded H on HF. Basically, it's just, this is like positive charge right here. Let's look at a different molecule, water versus I2O. In I2O, you notice you get this, still get this partial negativity over here, some slight partial positivity over on the edge. But again, because the lone pairs in I2O, it's not as partially positive. Whereas in water, you get this really nice differentiation between partially negative and partially positive, right? So hopefully these pictures show you why Estebovs are so important. It's because the magnitude of the charge on that H is not as strong. So what's wrong with the term hydrogen bonding? So Estebovs are very strong for intermolecular forces. So they're much stronger than typical dipole-dipole forces. Much stronger than dispersion forces. So water sticks together so strongly because it can make so many hydrogen bonds. Each water molecule can take part in 4 hydrogen bonds, which is why water is a liquid at room temperature, whereas other things its size are gases. All right, so we're very lucky that we have Estebovs. But these Estebovs are much weaker than a typical covalent bond. So compared to the other intermolecular forces, they're strong. Compared to covalent bonds, they are weak. And here's a nice little analogy. So if you think of this as your body, a covalent bond is like a joint in your body. Let's say your elbow. Right? So your bones are stuck together by this joint, by all that the ligament cartilagey stuff. An Estebov hydrogen bond is like 2 people holding hands. Now, I would argue in most cases, if you're trying to pull 2 people apart that are holding hands, you are going to split the people holding hands before you pop someone's elbow out of its joint, right? So the hydrogen bond is like 2 people holding hands, whereas the covalent bond is like a joint, right? The Estebov is going to split before the covalent bond. Now, what about, I mentioned biology earlier. Now, it's extremely important because they hold the strands of DNA together. You'll learn about how DNA unzips, unfolds, all these things next year. But the Estebovs, or hydrogen bonds, are what hold them together. And they make proteins fold up into the right shape to do their jobs. Proteins are very sensitive, and your body uses them a lot. They're called enzymes a lot in your body, but there are also other proteins. If they're not in the right shape, they don't have the correct function, and they will no longer work. So the hydrogen bonds actually hold the proteins in their right shape to work in your body. So they are extremely important for biology. Okay, intermolecular forces summary, last slide. If you are looking at a molecule, so really, I'm going to do a little flow chart here that helps you decide the type of intermolecular forces. Is the substance ionic? So yes. Well, then it's ion-ion, and we haven't really talked about this much. No, I'm assuming we're leaving metallic out of this. All right, that's ion-ion. We have another question. Is the substance polar? So if no, then dispersion forces are the intermolecular force that holds them together. This is yes. Is H bonded to O and yes, well then we have Estebofs. If no, we have dipole forces. So this is just a simple flowchart that helps you figure out what type of intermolecular forces are present. I do expect there to be a lot of questions for this, so please, I'm hoping that you're using the Google form to let me know the questions. But summary, you're asking, is the substance ionic? If yes, well, then you know it's ion-ion holding it together. That's very strong. Is the substance, if not, is the substance polar? If the substance is not polar, you know dispersion forces are the only thing that holds those molecules to other molecules. If it is polar, then you have to ask, is H bonded to O, N, or F? If yes, you have Estebofs holding the molecules to one another. If no, you have dipole forces holding the molecules to one another.